Today in the workshop, we're testing 3 air pressure sensors. You'll see how to use these sensors with 3 different microcontrollers and how to program them in C++ and MicroPython. We'll also run them together to see how they compare. We're feeling the pressure today, so welcome to the workshop. Well, hello and welcome to the workshop, and today we are going to be taking a look at some sensors that can measure the pressure of the air around you. Now, air pressure readings aren't something you think about as much as perhaps temperature and humidity, but you will find air pressure readings as part of your weather forecast because it's used to forecast the weather. Air pressure readings are also useful if you're engaged in marine or aviation activities, and there's a direct correlation between the air pressure and altitude. Now, today we're going to take a look at 3 different sensors. All 3 of them are on Adafruit modules, but the sensors themselves are made by different manufacturers. A couple of them also measure temperature and humidity. We're going to check out their performance with a number of different microcontrollers today. But first we're going to start off by learning a bit about how we measure air pressure. Air pressure is defined as the weight of the air in a column above a given area or point. At sea level, the air pressure is 1013.25 hectopascals. This is also known as 1 atmosphere. As the altitude increases, the air pressure drops because there are fewer air molecules to push down upon you. The standard measurement unit for air pressure is the pascal. A pascal is a very small unit, and so we usually use hectopascals. 1 hectopascal is 100 pascals. You'll also find air pressure expressed in millibars. A millibar is the same as a hectopascal, so 1 millibar equals 1 hectopascal. Here's a table that shows the relationship between different units of air pressure measurement. Air pressure is measured with barometers, and 2 gentlemen are responsible for the invention of the most popular types of barometers. Evangelista Torricelli, who invented the mercury barometer in 1643, and Lucien Vidi, who invented the aneroid barometer in 1844. A mercury barometer uses a glass tube inverted into a dish of mercury. The air pressure on the dish causes the mercury in the tube to rise. An aneroid barometer consists of a sealed metal vacuum capsule that changes shape under air pressure. The shape of the capsule drives a needle. There are 2 modern forms of air pressure sensor, the piezoresistive sensor and the capacitive sensor. The piezoresistive sensor changes resistance in response to air pressure, whereas the capacitive one changes capacitance. These days, all modern air pressure sensors are MEMS sensors. MEMS is an abbreviation for microelectromechanical systems. A MEMS sensor integrates mechanical and electrical components onto the same silicon chip. MEMS sensors can use piezoresistive, capacitive, or piezoelectric elements in order to sense air pressure. We'll be working with 3 different MEMS sensors today: the MS8607 from TE Connectivity, the BME280 from Bosch, and the LPS25 from STMicroelectronics. Let's start working with them. Okay, so let's get started testing our air pressure sensors. The first one we're going to test is the MS8607. This is a very simple device to use. It's an I2C device. It also measures temperature and humidity as well. And so let's go hook it to a microcontroller and check it out. The MS8607 is an inexpensive yet high-performance sensor. It's capable of measuring air pressure, temperature, and humidity, and for all of them it gives reasonable accuracy and range. This is an I2C device. In addition to the connectors on the side, it has 2 quick connectors for easy I2C connections. The connections on the side are as follows. V-in is the power input. Although this is a 3-volt sensor, as all of our sensors are, Adafruit has onboard regulation, so you can use this with anywhere from 3.3 to 5 volts DC. 3VO is an output from that onboard regulator, and it can provide 3.3 volts at 100 milliamps. GND is of course the ground, SCL is the I2C clock line, and SDA is the I2C data line. We're going to be testing out our MS8607 with a Arduino Xiao ESP32S3 board, but you could use pretty well any microcontroller for this. We'll connect the Xiao's 3.3 volt output to the V-in pin on the MS8607. The Xiao's ground will be connected to the sensor's ground. Pin D5 on the Arduino Xiao will be connected to the SCL pin on the MS8607, and will connect pin D4 to the SDA pin on the sensor. And this completes our wiring. Let's go take a look at some code we can use with the MS8607 air temperature and humidity sensor. And here's a simple sketch that we're going to be using to demonstrate the MS8607 air pressure sensor on the Arduino Xiao. Now, the sketch has been made simple because of a library that Adafruit has provided, the MS8607 library, and you'll need to load that within your library manager. So just go in the library manager and type in MS8607 and choose the Adafruit library. Once you've done that, it's a very simple job of getting some data out of it because the library does everything for you. We start by including the required libraries, the wire library for I2C and that Adafruit library, and then we create an object for the sensor. We go into our setup. We set up the serial monitor and we start I2C over here, and then we print to the monitor and we start off the sensor, and as long as we find the sensor, we'll print out that we've been found and we'll move on to the loop. In the loop, we define a sensor event with pressure, temperature, and humidity, and then we just go and do the get event from the sensor in order to get those values. As long as we have valid values, we will print them out to the serial monitor, and that's it. We'll delay a second and do the whole thing over again. So it's a very simple sketch thanks to the library. Let's load this up and watch it work. And so I've loaded everything up to the Arduino Xiao, and as you can see from the serial monitor, it is doing exactly what we want. It's displaying the temperature, the humidity, and the air pressure. So as you can see, this is a very easy sensor to work with. It's an I2C sensor that wires up very nicely. It is inexpensive. It has a library that makes it simple to work with in C++. It's really all that you need in order to display temperature, humidity, and air pressure in your next project. The BME280 is a classic sensor. We've used it before in a couple of projects here. Like the previous sensor, it also senses temperature and humidity as well as air pressure, but this one can also communicate on the SPI bus as well as the I2C bus. Let's go and take a look at this versatile sensor. The BME280 is a very popular sensor. It's capable of sensing air pressure, temperature, and humidity. And for all three, it has a relatively good degree of accuracy. This module can be connected using either SPI or I2C. For easy I2C connections, the module has two quick connectors. It also has pins on the side, and they are as follows. The V-in pin is the input voltage, and this can be anywhere from 3.3 to 5 volts, as the sensor will work on both. The 3VO pin is a 3.3 volt 100 milliampere output from an internal regulator. GND is of course the ground pin. The SCK pin has dual duty. In SPI mode, this is the clock pin. In I2C mode, this is the SCL line. SDO is the SPI data output. The SDI pin also has dual use. In SPI mode, it's the data input, and in I2C, this is the SDA line. And CS is the SPI chip select line. Today we're going to use the BME280 with a Raspberry Pi Pico 2, but any microcontroller would work with this. We'll connect the 3.3 volt output on pin 36 of the Pico 2 to the V-in pin on the BME280. We'll connect one of the Pico's grounds to the BME280 ground, and you can use any of the many grounds on the Pico. The Pico's default SCL pin on pin 7 will be connected to the SCK pin on the BME280. And finally, Pico pin 6, which is the default SDA pin, will be connected to the SDI connector on the air pressure sensor. And this completes our wiring. Now let's go and take a look at some code we can use with our BME280. And so here I have my Raspberry Pi Pico 2 connected to the BME280 sensor and a solderless breadboard. Looks pretty typical for an experiment here, but now when we go to the IDE, we're going to see that it's not the Arduino IDE. We're going to run this in MicroPython. Now running Adafruit sensors in MicroPython isn't always the easiest thing because Adafruit provides CircuitPython and Python examples, but no MicroPython ones. However, there's a second-party library that's available that you can use for this. And on the article that accompanies this video, I've got information about downloading that library from GitHub and renaming it because you'll need to rename the library. There are two different ones. But the easiest way to do this is also to download the code samples, also from the same article in which I've got the library for you. But at any rate, this is the library over here, and obviously it wasn't written by myself. It's basically a modified version of a Python library for the BME280, and it's made for MicroPython. And so here's the MicroPython sketch we're going to be using, and it's a pretty simple sketch. We're going to import the I2C library that's already in machine. We're going to import the BME280 library and time. And then we're going to define the pins for I2C and the frequency, and we're going to set it down because the Pico 2 can run at 400,000. That's a little fast for this, so we're going to bring it down over here. We're going to do a quick scan just to make certain everything is there, and we're going to set the BME object up over here, and then we're just going to get the values off of it, the temperature, the pressure, and the humidity from the BME.values, and we're going to print them out. And that's basically all there is. So if we run it right now, we'll get the scan, and we get the temperature, the air pressure, and the humidity, and it just continues to go in the shell right now. So this is a very simple method of using the sensor with MicroPython. So a different example, of course, there are C++ examples available with the library that you can download in the Arduino IDE. But either way, this is a very easy sensor to use. The LPS25 is a very high precision air pressure sensor, and unlike the previous sensors, this one only outputs an air pressure reading. It actually does have an internal temperature sensor, but that's only used for its own internal calibration. Now this sensor is very similar to the BME280 in that you can communicate to it with both I2C and SPI, and it's mounted on a similar looking Adafruit module. Let's go and check out this high precision sensor. The LPS25 is a high-precision air pressure sensor. The device only measures air pressure, but it measures it over a wider range and with much higher resolution and accuracy than the other two sensors we've looked at today. The LPS25 module from Adafruit uses both the SPI and I2C bus. As with our other two modules, it has two quick connectors for easy I2C connections. The pinouts on the side are as follows. V-in can be anywhere from 3.3 to 5 volts DC and should be at the logic level of your microcontroller. The 3VO pin is an output from an internal regulator that you can use for powering small things. GND is of course the ground. The SCK pin has dual duty. In SPI mode, this is the clock, and in I2C mode, this is the SCL line. The SDO pin is the SPI data output. SDI is the SPI data input, and it's also used as the I2C SDA line. CS is the SPI chip select, and INT is an interrupt output. Today we're going to be using the LPS25 pressure sensor with an ESP32C6, but you could use pretty well any microcontroller. Although we've used I2C for our other demonstrations, let's use the SPI bus to hook this one up. We're going to connect the 3.3 volt output of the ESP32 to the V-in pin on the LPS25. The ground of the microcontroller will of course be connected to the sensor's ground. GPIO pin 6 will be connected to the SCK pin. GPIO pin 2 will go to the SDO pin, and GPI pin 7 will go to SDI. Finally, we'll use GPIO pin 10 for our chip select on the LPS25. And that completes our wiring. Let's go and take a look at some code that we can use to use the LPS25 in SPI mode. And here's the code that we're going to be using with our LPS25 sensor connected up in SPI bus mode. And SPI bus is really just about the same as coding for I2C. You just use a different library and you don't need to worry about addresses. And it's very simple code. We'll include the required libraries, and that includes the Adafruit LPS2X library. And that is another library that you'll need to install through the library manager in your IDE. The SPI library is already included with the IDE. Then we define the different pins that we're using, and these are the connections we've used to the ESP32. Chip select was our own selection on 10. The rest of these are pretty well the default pins on the ESP32C6 dev kit. And we'll create an object for the sensor like we have in our other code. And in the setup, we're just going to set up our serial monitor, get it started. We'll also start the LPS sensor, and so we'll make sure it starts. Otherwise, we'll print out that we can't find it and end everything. And then we go into the loop and we create an event, populate it with the pressure and the temperature, and then we just print that out to the serial monitor and delay by a second. So once again, some very simple code thanks to the Adafruit library. Let's load it up and see if it works. And here we have our LPS25 sensor connected up to the ESP32C6 dev kit. And it's a pretty simple arrangement. It has a lot more wires than an I2C connection because it's going by SPI, but otherwise it's all you need to do. There's no jumper or anything on the sensor that you need to set for SPI. If we look at the serial monitor, we're bringing back the pressure. We're also bringing back a temperature reading. And although it's not advertised as being a temperature sensor, it has one for internal calibration, and you can get the reading from that as well too. So you can use it as a temperature sensor if you wish. But otherwise, as you see, the code was very simple. The wiring is a bit more complex because it's SPI, but we could have also run this under I2C. I just wanted to demonstrate SPI because we don't use it all that much. And yet another air pressure sensor that we can use in our hobbies. Now, after using these three sensors, one obvious question is, how do these compare to one another? And that's a pretty easy thing to find out because these Adafruit modules all have quick connectors. The quick connector is an I2C connection that's very easy to use, especially if you have a microcontroller that has a quick connector like the Arduino Uno R4 Wi-Fi board. So I'm just going to connect all three sensors up to the Arduino Uno R4 Wi-Fi and write a little bit of code so I can read the air pressure and only the air pressure readings from the three sensors just to compare the readings to one another. And here we have our demonstration with the three sensors connected up to the Arduino Uno R4 board. And as you can see, the connection is very simple. I just used a quick connector on the R4 board and connected it to the quick connectors on the sensors, which are daisy chained. They're mounted on a solderless breadboard, but that's only to hold them down. The pins aren't connected to anything. If we go over to our serial monitor, we can see that the MS8607 and the BME280 are practically reading the same thing. The LPS25 is a little bit higher, and that's actually supposed to be the most accurate of the three sensors, so you can sort of take that into account. But all of them give very similar readings. I'd say that any one of these sensors would be a good fit for your project. And that about wraps up our look at air pressure sensors. I hope you enjoyed the video, and I hope that you've seen that air pressure sensors are really easy to use and you can add one to your project. Now, if you need some more information about air pressure sensors, or if you want to get the code that I use, check out the article that accompanies this video on the dronebotworkshop.com website. There's a link right below the video to the article. When you're on the website, please consider subscribing to my newsletter. It's not a sales letter, just my way of letting you know what's going on here in the workshop and sometimes giving you previews of my videos. And all I need is your email address to sign up for that. If you're willing to give me a little more than your email address, let's say make up a crazy username and give me your first name, then you can join the DroneBot Workshop forums where you can talk about air pressure sensors and all sorts of electronic devices with a number of like-minded individuals who can also help you out with your projects, and maybe you can help them. And of course, the forum is free to join. And if you're in a signing up mood, still, how about subscribing to this YouTube channel? I make videos about electronics and microcontrollers, and if you like this video, you'll probably like the other ones. It's really easy to subscribe. I'm sure you know how. All you need to do is click on the red subscribe button, but if you also click on that bell notification, you'll get notified every time that I make a new video. So until we meet the next time, please take good care of yourself, stay safe out there, and I'll see you soon here in the DroneBot workshop. Goodbye for now.